So I'm going to be talking about passivation approaches for high efficiency photovoltaics. I thought as the first speaker in this symposium, I'd like to provide a little bit of broader context of why we're doing all this and what's happening. So this slide shows you what's happening in terms of global annual new capacity per year. So this is what we're installing around the world. And the exciting thing you'll find is that we're installing more photovoltaics than anything else each year now. This is a really big change over recent years. You can see this has only happened in the last 5 or more years, but we're now putting in more photovoltaics than anything else. Second is wind. So this is very exciting. I don't know if Anita remembers. I certainly remember when we were very excited when photovoltaics had just passed nuclear at that time. And so we've come a long way since then. And this is happening because solar is actually cheaper than coal now. So this is data for Australia. The cost of solar and wind is cheaper than anything else to install. And also cheaper than anything else, including when you have some battery or some pumped hydro storage. So this means essentially that the installation of renewables is unstoppable now because it makes sense purely on economic terms. That means everything that we're doing for the most important energy technology. So we are developing now the most important energy technology in the world. And solar is a big business. Of course, we have to keep that in mind for everything that we're doing. If you look at how silicon modules are installed, we're talking about gigawatt scale factories. We're talking about a cell per second. We need to always keep this in mind whenever we're thinking about any kind of production of solar cell technology. And the exciting thing is we're now actually starting to put in enough solar that it's at a scale that's significant enough to have an impact on climate. So the installation of photovoltaics has been growing at an average of about 38% per year. This is an incredible number. Anytime you think about anything growing, you usually think in the terms of 5% per year. But this is how it's been growing. It's been growing to the scale where we're looking at 100 gigawatts per year or so now globally. This is 1/10 of a terawatt, and terawatts are the scale that we need to be installing if we're going to have a significant impact on climate. So overall, what's happening now is at a large enough scale to start to have an impact on climate. And we have to think a little bit more broadly than that as well, because people have been talking mostly so far about electricity in terms of what electricity does, but we're changing, of course, what we use electricity for. So electric cars are now cheaper to run than petrol cars, and now, of course, they can be cheaper using renewable electricity. Reverse cycle air conditioners or heat pumps is now cheaper than gas and can be cheaper than renewable electricity. So we're changing not only electricity, but we're changing the whole energy sector here. This is what we're doing with developing better and cheaper photovoltaics. And it doesn't stop there, because we can also change how we produce fuels. And the connection here is with the cost of electricity. So this graph shows you the price of hydrogen as a function of your electricity cost and as a function of your energy conversion efficiency. Now, electrolyzers, we should be very jealous of electrolyzers. They're extremely efficient compared to solar cells. They're something like 50 to 70% efficient already. So improving the efficiency of electrolyzers doesn't help very much. But what you'll see is that reducing the electricity cost even further actually starts to make hydrogen profitable, right? If you're producing it from renewable energy. So we've said that solar energy is already cheaper, but if we can bring it down even cheaper, then we have the possibility to make fuels using renewable electricity as well as just producing the electricity. So this is the reason why we need to keep going down this path of making solar cells more efficient and cheaper. Okay, so how do we do that? If you look at a silicon system, you can break down the cost and you can see that your actual silicon, your actual wafer, your whole cell, your whole module, all of that is only about 25% of the cost of the system. So if you pick up your solar module, that's about a quarter of the cost as when you put it on your roof and it's all installed. This is quite surprising, but 3/4 of the cost comes from the balance of systems, the inverters, the mounting system, the cables, the labor, all of these sorts of things, right? So it's really important to understand that in terms of how you can reduce costs further. You don't want to be just looking at the costs of the processing, you want to think of the entire system. What this means is that if you have a higher efficiency system, you have a reduced area. That means you need less panels, you need less installation and labor, balance of systems, mounting hardware, all of these things. If you have a higher efficiency system, you need less of them. And so that reduces your cost overall. So this is overall the justification for your higher efficiency system. It's not about the just efficiency per se, it's that efficiency is going to give you a cheaper system altogether. Okay, and so there has been this trend that we see towards higher efficiency. You can see it in the transition away from the back surface field to the PERC pearl structures in the orange. You can see it in the expected transition to heterojunction as well as into the silicon-based tandems. And of course, the leading contender for the silicon-based tandems would be the perovskites. So we can see that this is in the industry roadmap shows that expectation of that move that will go on towards higher efficiencies. But if you look at the research cell efficiencies, the thing, of course, that always jumps out at you is that the silicon cells have stayed pretty much constant in efficiency over the last 25 years or so. And that's fundamentally because of the properties of silicon. We're already very close to the limits of the efficiency of silicon. There's really nowhere very much to go in terms of increasing the efficiency of silicon cells themselves. On the other hand, with perovskites, we have a lot of scope. They've been improving in efficiency further. We're getting to quite high efficiencies now, but we can further improve those efficiencies. But also beyond that, we have the possibility to make tandems, which we didn't have with silicon photovoltaics. Okay, so that's all by way of justification. This is why efficiency is hugely important, increasing the efficiency of perovskite solar cells. And we know that the interfaces are really the key limiting factor for increasing the efficiency. So what we have to do is improve the interfaces. So what I'll talk about in the rest of the talk is a number of strategies that we've been using to improve the interfaces with various passivation techniques. So this was some of our earlier work looking at passivation of perovskite solar cells. So what we were doing here was a combination of PCBM and PMMA. So you can see here we have an NIP perovskite solar cell, and we have this ultra thin passivation layer between the titanium dioxide and the perovskite. And what we found is that when we included the PMMA layer by itself, it certainly improved the voltage, so that helped, but it led to a reduction in fill factor if you only have PMMA. So what we did was we had a combination of the PMMA and the PCBM, and we found that by doing that, we could increase the voltage, but also have an increased fill factor and overall higher efficiency by having that combination of PMMA and PCBM. And the reason is that the PMMA is insulating and the PCBM is conducting, and so that allows some conduction that allows some balance of passivation and conduction by using that mixture. So we moved on from there to a double-side passivation approach, and this was applying a PMMA layer to the other interface in this case. So this was at the interface of the spiro layer and the perovskite. We're able to get a high voltage for that. And what we found is that the PMMA provides passivation of defects on the perovskite surface. So this was via a combination of FTIR, NMR, and DFT. And overall, that allowed us to conclude that the PMMA was passivating defects on the perovskite surface. Now, the interesting thing was it worked for a range of different perovskite compositions. So we tried this with a number of different perovskite compositions, and in each case, we're able to get a passivation effect. So that was very important in enabling us to just get a higher efficiency overall for any type of perovskite solar cell that we wanted to make. So recently, we've developed this further, and what we've looked at is a nanorod structure. So what we've got here, if you look at the top left, we've got some titanium dioxide nanorods, right? And a combination PMMA PCBM passivation layer on the bottom, and this defined nanorod structure. And you can see it here in quite clearly in the cross-sectional scanning electron micrograph. And what we see is that especially this structure leads to a significant improvement in fill factor. So you can see we were able to get very high fill factors overall, a certified efficiency of 21.6% for a 1 squared centimeter cell. So this is a relatively large cell, and that had a fill factor of 0.839. So in order to understand what was happening in this device, what we did was to do some 3D numerical modeling, and the structure is shown in the top right there. So this is an element of the cell showing the nanorod, and what we modeled it as the nanorod was partially covered by a passivation layer. So about 30% of it is uncovered and the rest is passivated. And then what we did, we can vary the pitch there, so that's spacing between the nanorods. And we also varied the ratio of the recombination at the bare and the passivated layers. And you can see that what we found is that we've got a very good fit to the results when that bare area in the yellow had about 10 times the recombination of the passivated layer. And in that case, that provided very good explanation of why we had particularly good results for the 300 nanometer pitch. And you can see that we have good agreement there between the experiment and the simulation. And particularly what we see is that increase in fill factor by having the combination of the passivated areas and the unpassivated areas. So again, that provides that balance between the areas where you have reduced recombination, but it also allows you to get that good electron transport into the bare regions. Now, interestingly, there are other ways to achieve that. So what we're doing here is a quite different approach, but the net effect is actually very similar. So here we've got a perovskite layer that's passivated with a mixture of N-butyl ammonium iodide and isobutyl ammonium iodide. So that's what the DIAC means. That means the mixture. So we compared the cases where you're passivating with N-butyl ammonium iodide, where you're passivating with isobutyl ammonium iodide, and where you're passivating with that mixture. And what we found using UPS measurements is that you have a change in the fraction of 3D perovskite that's on the surface and 2D perovskites that's on the surface. So especially with that dual layer, then you have more 3D perovskite on the surface and less 2D perovskite on the surface. So the overall net effect is that you have these 2D coated areas that give you effective local chemical passivation, but you also have this partially exposed 3D film to provide a conductive pathway. And again, what we see in this case is you have a significant improvement in fill factor, and as a result, a significant improvement in the efficiency. And in this case, we had an efficiency of 23.3% on a small device. All right, so that's some results on passivation. I'll just talk briefly now about our application to tandem cells. Of course, the advantage of a tandem is to make better use of the blue light. In a standard single junction cell, you use the blue light quite inefficiently. So in a tandem, you can have a higher band gap cell on the top and use that blue light much more efficiently. So we've looked at a range of different types of tandems, but in these results, I'll talk about a 4-terminal tandem. So we're having then a perovskite cell on the top connected independently with a silicon cell underneath. So in this kind of configuration, we were able to combine a perovskite top cell with a silicon bottom cell. This perovskite top cell by itself had an efficiency of 17% for the semi-transparent cell. Combined with a silicon bottom cell, we're able to get an efficiency overall of 27.7%. And when we did that for a size matched the case, that was 26.2% for a size 1 centimeter square size matched 4-terminal perovskite silicon tandem. And again, the key to this, in this case, also was the passivation. So we used passivation with the N-butyl ammonium cation. And what you can see here is that we compared putting this material in the bulk or on the surface. You can see from the photoluminescence images that you have a very high photoluminescence when the material is on the surface. And you can also see in the top left that we have lower traps from those current measurements as a function of temperature. So you can see particularly the red case is reduced, showing that the surface low concentration. You show definitely reduced traps compared to the control case. I just want to finish up briefly with talking about solar hydrogen generation, because I mentioned the possibility of hydrogen generation and how you can actually make hydrogen generation cheaper. There are a range of sort of different ways of doing this, but the perovskite tandems are particularly nice because you can get the voltage that you need for water splitting very easily. And there's a range of different types of ways to do that. But I'll just sort of show you some of our initial results in this direction. So what we've done is we've connected a perovskite solar cell together with a silicon photocathode. Now the perovskite cell is kept separate, and the silicon photocathode is integrated into the electrolyte and then produces hydrogen and oxygen. So in that way you split water. And the important thing is that with this configuration, you can get the voltage that you need, because the minimum theoretical voltage for water splitting is 1.23 volts. So the perovskite and silicon combination is very nice for giving you the voltage that you need. Always with these situations, you have an overpotential. So the voltage that you have from the tandem is actually very well matched to the voltage that is required in practice for water splitting. So this shows you results. We integrated a silicon photocathode with a perovskite cell, and overall we're able to get an efficiency of 17% for solar to hydrogen generation using that combination of the perovskite and the silicon photocathode. So just to conclude, we've said that there's more solar being installed annually than any other technology. It's the cheapest thing to install at the moment, but this is not the end of the game, because further cost reductions enable a lot more. It's going to be the largest energy technology overall, and for that reason enough, it's worth continuing to reduce the cost. But further cost reduction also opens up new opportunities for solar, especially in the production of hydrogen. We've reported a certified efficiency of 21.6% for a 1 square centimetre cell using this passivation approach with titanium dioxide nanorods. And this passivation approach is very general, actually. It's that balancing of passivation with charge extraction. So in this particular case, we've done it with titanium dioxide nanorods. As I showed, it's also possible to do that with combinations of passivation materials. So there's lots of different ways of doing it, but overall, it's a very effective strategy, especially for increasing the fill factor of these materials. And with that, I'll thank you and pass back to Anita.